Good evening, and welcome to Making Michigan, the Bentley Historical Library's series on the history of the University of Michigan. I'm Andrew Rutledge, Bentley historian and research associate, and I'm pleased to welcome you all tonight to the historic Judy and Stanley Frankel Detroit Observatory, a division of the Bentley. I also want to welcome our online audience on YouTube. Thank you all for joining us on this really beautiful fall evening. Tonight, we have a very exciting and, considering our location, deeply relevant talk. The Detroit Observatory was built in the 1850s with the goal of launching the University of Michigan to the forefront of astronomical and scientific research. And I think it's safe to say that it succeeded in that goal. But it was also a place for education, initially solely of university students, but also, as this new exhibit shows, at times the general public. But today, its purpose is exclusively one of education, sharing the history of the university and of astronomy. But the Detroit Observatory, of course, is not the only place on campus that seeks to share the amazing discoveries and workings of science with the broader public. And tonight, our speaker, Timothy Chupp, will discuss the history of one of U of M's most successful public science programs, Saturday Morning Physics. For 30 years, this program has hosted monthly sessions exploring the hundreds, if not thousands of ways physics impacts all of our lives every single day. With speakers drawn from multiple departments across U of M, it has also demonstrated that while science is a human endeavor, and thus as prone to error as anything else we humans do, there's nothing that should ultimately be trusted more. For in the end, nature always tells the truth. Plus, I'm going to say, I think live physics experiments are always super exciting and fun to watch. Now, our speaker tonight, Timothy Chupp, is professor of physics and biomedical engineering at the University of Michigan. After earning his PhD at the University of Washington, he began a research career focusing on particle physics. Most recently, his team has helped develop a new technology to assist MRI machines in measuring blood flow in the human brain. A fellow of the American Association for the Advancement of Science, he is also devoted to public outreach and popular science, and has helped organize Saturday Morning Physics since its founding in 1995. Please join me in welcoming Professor Chupp.
Sorry. Thank you so much, Andrew. That was a lovely introduction. It's really an honor to be here and to be the one to review the history, 30 years of the history of this amazing program here at the University of Michigan. In the physics department, as I will relate, sometimes I think it should be named Saturday Morning Not Just Physics, and we'll show you why. But we've been here for 30 years. This is our 30th anniversary. In fact, it was in the fall, October of 1995, that the very first lectures took place. And over its history, I would say that it has found itself, the program. And I can now put together this, what do you call it when you have 4 words all starting with the same letter? On a minute. Alliteration, yeah, okay, fine, thank you. Engaging, educating, entertaining, and exciting the public about science and technology in its many, many manifestations. So, I recognize some of you. I don't know who's online, but the people here in the room, who's been to Saturday Morning Physics regularly or a few times? You see the hands go down. Just once? And never? You're willing to admit? Okay, well, you need to come. But why? So we check all that apply. And you can raise your hands if you like, but one of those is, what else is there to do on Saturday mornings? When I was growing up, we watched cartoons. That's the engaging aspect, right? It's fun. It is fun and entertaining. It could be that I love learning. I've loved learning all my life, and I'm doing everything I can to take advantage of educational opportunities. And also, we do demos at Saturday Morning Physics. I'll show you a few of them here today. And many people think they're exciting or intriguing or surprising and educational. So I guess I should tell you who I am. I have been calling myself different things. And one thing I didn't learn how to do really, really well was spell. So you can point those out to me. Take notes, please, and then afterwards let me know. So I am a physicist, and I now call myself a quantum engineer because it's exceptionally important to understand how we are exploiting the quantum nature to do what we do in many, many different ways in science and technology. What we do is we measure the magnetic and electric properties of particles. The particular particles are called neutrons. You may have heard of those. And muons, which maybe are a bit more exotic, but they're everywhere. And we use quantum sensors that are based on quantum properties and quantum energy levels to help us make these measurements. I also have been focusing my teaching over the past, 30 years mostly, but certainly the last decade, on two very different kinds of courses. One is called Everyday Physics, and it's for non-science majors. I'll tell you more about the notions of everyday physics today. And more recently, I've been teaching a somewhat technical course on instrumentation to advanced undergraduate and graduate students. And as Andrew mentioned, and it's been my honor to have been involved one way or another with Saturday Morning Physics for the entire time. So how did I get here? Where here is at the University of Michigan, but also to be able to call myself those things professionally and have this involvement and this great privilege of being a University of Michigan professor or a college professor, where I get to do research, teach, and it's my own choice, but enjoy public engagement. So I grew up with a family of scientists, actually more generations. My grandparents, my parents, they were all scientists. And they wouldn't let me escape, right? I tried. So for one thing, the house was filled with stuff I could take apart and sometimes put back together, as my father often reminded me. I don't know if you've heard of Heathkit, but there's a company in Benton Harbor, other than Whirlpool, called Heathkit. And for people of my generation, the Heathkits were, you could just get this box filled with parts, electronic components, and put it together and learn how to construct it, maybe troubleshoot it. I remember one of them we actually sent back to Heathkit because we couldn't get it to work, not even me and my father. But this really was one that I built. I found this picture of this Heathkit. This is the inside of it. It's a crystal radio. And this is a headset for the crystal radio, and it came with this nice manual and all of that. That's not the first crystal radio I built. The first one I built, we used, this is called a coil or an inductor. And the first one, actually, we used the inside of a toilet paper roll and wrapped wire around it. At any rate, they gave me a chemistry set, which I wasn't very good at. That's why I became a physicist. And I still have lots of parts of bicycles, I have to say. I did take apart a couple of clocks, and I think I put at least one of them back together. So not only was there all these things to play with, but also the family, we just talk about big questions from time to time, like questions about the universe from an early age. So I have wondered what people think when they hear the term a big question. Like, you know, what's a big question? So I asked a few people, family and friends, and I don't know if you can read this, but how big is space? They made these, you know, they said, oh, I really want to know, how big is space? That's a really big question, right? How will the world end, I'm afraid? The when is probably a more pressing question these days. But, and do cats know their names? It's a daughter of a friend of mine. So those are examples of really big questions. My big questions are, what are the smallest pieces of matter and how do they fit together? So that's what particle physics is in a sense. And also, where did all the stuff in the universe, stars, planets, people, and cats, where did it come from? And you know, my daughter, when she was about 12, asked me what I do. And after about 20 minutes of me trying to explain, she interrupted and said, "Oh, so you're trying to find the origin of matter." As simple as that. Eloquent. What does that mean? Well, what is stuff made of? I like this example, and I've used it with audiences at all levels. It's a tunable example. So any other particle physicists out there want to kind of explain, or not necessarily just particle physicists, right? What's a rock made of? What is this rock made of? I will tell you that it's granite. It's a kind of granite. I grew up in New Hampshire, which is the granite state. So I saw a lot of this growing up. What is it made of? Okay, so how do you answer that question? Right? It kind of depends on your perspective. Does anybody want to help me answer that question? Okay, right. Okay, that's very good. So he's telling me about the minerals that are in the rocks. It's a quartz, feldspar, mica. Yep. Are you a geologist? No. But that is how a geologist might answer that question, right? I'm not sure who would answer it by it's made of smaller rocks, right? Of course, right? At least you could take it apart and make sand. So it might be a mason who does that. And then the geologist would think about what the minerals are that are in here. And that's what I had to learn when I was in third grade. Quartz, feldspars, and mica. But what's quartz made of? Right? What is feldspar made of? What are smaller pieces? Still, well, a chemist would, apparently that's what a chemist looks like, by the way. I got the chemistry set, and you can tell that it's because of the chemicals, right, that they have no hair there. This is silicon dioxide. It's one of the most common minerals on Earth. It's basically the main component of sand. Glass is made from sand, etc. These are feldspars, aluminum oxides, and so on, and iron. These symbols, of course, represent chemical elements. And a chemist would maybe even say not just what the molecules are, what are the compositions of the minerals, but what are the atoms, okay? So granite is made of atoms, no question, right? That's when I ask that question of sort of K through 5 students, that's what they come up with, because they think that's the answer I want, right? But I don't want any specific answer. I'm telling you any of these answers are good. Here's a picture that you may have seen, a rendition of an atom. Here's another quiz question. Okay, that is maybe the first. What atom is that? It's got 3 electrons, and it's neutral. The red things are protons. I don't know. So it goes hydrogen, helium, lithium. At any rate, yes. And it's got 4 blue things. And what's at the center of the atom, of course, is the nucleus. Right, so that's a picture that is pretty common. It depicts a lot. It's effective because it shows that there's a nucleus. It shows that the electrons, in a way, are in motion, and also that the electrons are actually not, the nucleus is more compact. It's at the center. But there's something really, really wrong with this picture. And that is that the nucleus is way too big. You know? So I'm going to show you a picture of the room that we normally do Saturday morning physics in. In that room, which is probably about 20, 40, many tens of times bigger than this room, the tip, the point of a pencil would be the nucleus if the electrons are occupying the entire room. Or maybe, since we're here, you consider Michigan Stadium, which is about 300 meters across if you consider everything or so. So that's the number I use. And we have to zoom in and zoom in and zoom in and zoom in to about a centimeter. A fraction of a centimeter at the center of Michigan Stadium would be the size of the nucleus. And so that's a really interesting thing to know, that you tell your friends now. That, that picture is effective, it's accurate in certain ways, but we can be more accurate by considering the difference in the size. Okay, so I'm actually going to skip this to get to Saturday morning physics. But I'll tell you that the other big question is, what's the origin of matter? And I'm just going to say, because I have this slide, that in the early universe, the very, very earliest instances, we don't know the units to use, instances at the beginning of the universe, before the particles that we know today, neutrons, protons, electrons, for example, or even their constituents, existed, the universe existed. And in that universe, there was the same amount of, now I'm going to use the term matter, okay, but the reason I use that term is matter is, universe is made up of matter, because there was also antimatter. In these very early instances, there was equal amounts of matter and antimatter. Today, there aren't, because if there were, you may know this, that matter and antimatter come together and annihilate. No more particles, no more matter, no more antimatter, just energy, and nothing to make neutrons and protons and electrons and stars and planets and cats. So we don't know why or how, but we do know some of the elements of that, and those were given to us. I'm sorry, this slide's a little weird, but it was Andrei Sakharov, who's best known as Soviet dissident, and spent many, many years in prison for his dissent. And he gave a recipe. And that recipe includes the features of the universe, which was kind of like foam. But you think about foam, and foam is made up of bubbles. And those bubbles sometimes overlap and coalesce, but the bubbles are all different. That's why the foam is white, by the way. So the bubbles are all different sizes, like on a bubbly drink, right? Like a carbonated beverage or something like that, at least whitish. And then when they come together, and at some point there's something that we in physics and science call a phase transition. It's not unlike sugar crystallizing in a solution, or if you're trying to, the caramel is too hot and it crystallizes. That's a phase transition. It changes from a liquid into a solid. And when that happens, things get frozen in, the differences get frozen in, and if that difference is spontaneously more matter than antimatter, then that can explain it. But the science that does that would also cause a property of a particle that we can measure in the laboratory today, which is an electric property of a neutron in particular. So that's why I'm doing that, and that's why I say that I'm trying to find the origin of matter, or at least contribute to that problem. So back to making Saturday morning physics, 1995. Dan Amadei, who's a professor in the department now, was an assistant professor. He had just arrived after spending his postdoctoral research years at Fermilab. Fermilab is a laboratory outside of Chicago, which was the premier in the world particle physics laboratory. This is a above ground service to below ground tunnel that's on the order of a mile across, and protons go through one, and then there's another one over here, and antimatter, the antimatter partner called antiprotons go through, and they collide. So this device is called a collider. And when these protons and antiprotons come together, they have sufficient energy to produce many other particles, which then are studied. And there were many discoveries done there. And one of the great leaders of the lab, not the first leader, Robert Wilson, but Leon Lederman, a Nobel Prize winner, and also an author and a man with a tremendous sense of humor who could tell jokes. But the only jokes I remember he told, I can't tell you, I'm afraid. Um, but I've been practicing one, but I just realized I couldn't tell it here. And he wrote, just to give you a sense of Leon Lederman, he wrote a book called The God Particle, just to describe the fact that there was this one thing, you may have heard of it, called the Higgs boson, which was subsequently discovered not at Fermilab, but in Switzerland at CERN, the actual physical particle. But it had been sought, and its role in explaining how the smallest pieces of matter that we know about fit together, it's been so essential for decades. So he wrote this book called The God Particle, and then it was discovered in 2012, and then he wrote, like, what comes next now that we've got this all figured out. I love this. If the universe is the answer, what is the question? So think about that. So Leon Lederman started a program at Fermilab called Saturday Morning Physics. And if you Google Saturday Morning Physics, you'll find that there are several other places, South Carolina, I think, Florida, use that term as well. We have the website name, SaturdayMorningPhysics.org, so we got there first, I guess. But at any rate, when Dan came here from Fermilab, where postdocs would give lectures and lead tours and so on at Fermilab in a program called Saturday Morning Physics, that it was like, what are we going to do Saturday morning, say all the high school students in Chicago? Well, let's go to Fermilab to Saturday Morning Physics. So Dan talked to our faculty about different ideas and different motivations. And one of the motivations was to give postdocs the opportunity to learn how to engage the public, give lectures, and talk about their research. So, and it was very ambitious. 3 lectures, which can take weeks, months even, to prepare in a way that can be suitable for a public engagement audience. And he also thought they should be on football Saturdays because, you know, people would be in town. He didn't think about parking, but that's actually been the most difficult thing about Saturday Morning Physics, believe it or not. It's a terrible thing about life that, you know, it's all about parking. At any rate, 3 lectures, football Saturdays, 1995. I thought you might want to remember the Michigan football season in 1995. I kind of remember it because it was Lloyd Carr's first year as coach. They went 9-3. They were ranked average of 18, I guess you might say. This is the coaches poll, which used to be the in USA Today. So Ohio State, they won. And the MVP, who still holds the Michigan rushing record, was Tim Biadabattuka. Practiced that as well. 18 yards. He was, I think, born in Zaire, actually. And it's really important to say that the University of Michigan president was James Duderstadt, who died last year, and did great things. In particular, not in particular, but he was a physicist and a member of the American Physical Society, and here in the nuclear engineering department, dean of engineering, provost, and then president. And had a lot to do with some of the luster of the physics department through the 90s and 2000. The first of these was by Dr. Robert Welsh, who was a member of my laboratory. Andrew mentioned this medical imaging. It's actually not very recent. But Robert talked about this, and he's now a professor of radiology at the University of North Dakota, so this was good for his career after all. This is what we were doing at the time, and we were doing it in a building that right across here that no longer exists, Kresge 3, with Scott Swanson, a graduate student, Matthew Rose, and Bernie Agronoff was a great member of the University of Michigan community for many, many years, and Robert. And so he gave 3 lectures about medical imaging and the work we were doing, where we convinced this animal, which is a rat. This is the head of the rat and sort of the normal image. I just want to point out that this is the eyes, okay, and the ears. And then the brain, well, it's a bit covered up, but it has this very, very large component of the brain that we really don't have, which is the olfactory nose. Node, the olfactory node. And, right, so what we did was we convinced the rat to breathe into its lungs xenon gas. Xenon gas has been back in the news because some climbers used it to crest Everest, to get to the top of Everest. Without oxygen, they used xenon to train their lungs. At any rate, the thing is that it started in the lungs, it got to the heart, got pumped to the brain. So we were tracking this throughout its journey, physiological journey in these small animals. So this was an interesting technique at the time. People are still doing this research. We're not strongly involved because it's been interesting, but not something that we've continued. So one thing about Robert's lecture and Dan's idea was that we didn't know how many people would come. So this is the room that was scheduled on Saturday, that was free on Saturday morning, scheduled on Saturday morning. Here, it holds about 40 people. It's a classroom in the physics building, and it started at 10:30, about 5 minutes before it was going to start, the entire hallway of West Hall, or which is called West Engineering at the time, was filled. There were more than 100 people who wanted to hear a talk on physics from Dr. Robert Welsh and imaging called Saturday Morning Physics on a Saturday morning at 10:30. And anyone here in the room was one of those people? You were there, yeah. So we had to delay the start because we weren't going to turn away anyone, right? But across the hall is what was called the Dennison Building, now the Weiser Building, and this has been this home of Saturday Morning Physics, the main home ever since, which holds about 250 people. So that's where we spend our time now. And so that was a really remarkable thing. It was just postdocs. It was just the fall for several years, but the program evolved. So within a few, and we actually are having we've tried to figure out exactly when this started, but the records have been very, very good for the past 20 years. But we don't know if it was 3 or 5 years. It's a little bit vague. If it was 5 years, then I gave one of the first faculty lectures, which were in the spring term. That's kind of what I looked like back then. And I gave a series, so that was 3, called Nuclear Magnets, from atomic clocks to medical imaging. So this is medical imaging. I showed you the rat brain work, so to speak. The atomic clocks use the very best clocks available, which are atomic clocks, and they only work because they are very insensitive. This is a little hard to see, but what we're showing here along the bottom is the magnetic field. And what we're showing here are the quantum levels of, in this case, the rubidium atom, but cesium was what's used in the clocks. And the curve here of the green one, you see that it's curved down here near 0 and curved here near 0. So if we pick those 2 quantum states, it's pretty flat and therefore insensitive to magnetic fields and can make a better, more accurate clock. So if it weren't for the magnetism of the nucleus, atomic clocks would not work the way they do. And then we also studied what is inside the neutrons and protons. Yes, question?
Are you the presenter that enlightened me that time flies like an arrow and fruit flies like a banana?
Oh, use the mic. So this is a good question. And
so I remember a presentation on time, and I'm wondering if you're
Yeah.
the presenter that enlightened me with the fact that time flies like an arrow and fruit flies like a banana.
You know, so the person who gave a talk on time, I happen to know, about 15 or 16 years ago, was Aaron Leonhardt. And I'll tell you more about Aaron in a little bit. He is not going to be giving a Saturday morning physics talk this fall, but he was scheduled to. He's now a professional baseball field coach, so consultant. So he's in baseball. All right, so who comes to Saturday morning physics? Well, you've come. No, I'm not that eloquent, by the way. Just all right, so this was a Saturday morning physics that I gave. The audience all got cards that had what are called diffraction gratings in them that separate light, dispersed light spatially. You could probably find yourself there. And we were looking at what we would call a spectrum, the characteristic lines of light, and they're called lines because that's how they appear when looking through these cards. By the way, the cards are supposed to be held horizontally. Yeah, so I started talking and I looked out and saw this, and I pulled my phone out and took a picture of this and brightened it a bit because the room was actually darker. So who comes? Well, there are techies of a certain age. We realize that. We used to say retired automotive engineers. But there are fans of all ages, depending on what we present and how we advertise it. Middle and high schoolers used to come. High schoolers for credit. I used to sign many slips for at least Ann Arbor and Ypsilanti high school students. Teachers come up and talk to me afterwards and ask questions or tell me about what they've been teaching. We have families, whole families that come, sort of, if Saturday morning physics existed in the town I grew up in, my parents would have made me go. Or I would have asked them, I would have made them go. We've had VIPs, the governor, et cetera, so not to emphasize too much, but a number of important persons, the head of science at NASA, for example, and just curious people, right? It just sounds interesting. We now advertise on Michigan radio, so, and when I get up on Saturday mornings, I hear the ads, and I go, well, you know, if I didn't have anything to do, I might go. And I do, because I have to go to Saturday morning physics. So, why? Well, the original idea was postdoc experience and engaging the public, and but in particular, it had that motivation of postdoc experience. We've been showcasing for 30 years University of Michigan research across the entire campus. I'll tell you more about that. It's community engagement. We've had, related to Saturday morning physics, Detroit area science teachers come, and we've shown them some of the things that we do for continuing education. It's important now, moving on to sort of another way of thinking about the public engagement aspect of Saturday morning physics, how scientists do science, to show that to a broad audience. The everyday impact of science and technology, the relationship of science to policy and public understanding and trust in science. So those last items are extremely important. They've been important to me for a long, long time. I've tried to get our program to address them in various ways, and I want to talk a little more about that. So how do scientists do science? Okay. Remember the scientific method? Right? It's pretty straightforward, but there's some really crucial things about it. Make an observation, right? So I like to call it measuring things, but that's the way I do it. But you know, in other sciences, observations are done in different ways. Make an observation, ask a question, form a hypothesis, which is a testable explanation for the observation. Make a prediction based on the hypothesis. That means it's testable, and then do it somehow. I mean, right? And so there's just any number of things to which this applies, and then do it again. and again and again. It doesn't end. Science is the thing that scientists do. Scientists are human. It's a human activity, and it has human weaknesses as well. And knowing that, it's crucial to always question the results. So, I want to say something about science, because I grew up hearing, for some reason, that physics was an exact science. There is no exact science. Have you heard that? Yeah. There is no exact science, right? So let me show you this kind of example of, it's a metaphor of two aspects of imprecision, I guess you would say, or at least imperfection, I'd like to say. Precision and accuracy. So I'm going to try to be precise about the difference in the meaning of precision and accuracy. Okay? So if you can see these red curves, these are what are called distributions. They represent, in some sense, how a set of measurements, which are shown here as hits on a target, where in some way, nature knows that the right answer is at the center of the target. Okay? We don't know that perfectly, but let's just say there is truth, and there should be. That's part of our belief in doing science, and that we're trying to get close to it. But we don't, because our measurements and our instruments are imperfect. So there's a distribution. And we'll only look at the horizontal part of this. So if I project those down here, there's a few more. If we did this a lot of times, we could get a kind of smooth curve here. But the important aspect of this curve is two important aspects, actually. One is that it's not quite average. The average of all of these is not quite at the center of the target. Okay, it's imperfect in that way. It's inaccurate. But also they're spread, and the spread is what we call the precision. Okay, less spread is more precise, but this particular set of more precise measurements is just not as accurate. Okay, so that's, at least if you compare these two, that's less precise, more accurate, and more precise, and that's indicated in this distribution, less accurate. So we can sort of make this grid. And you can think about lots of things, and you can just hold them up to this picture and be precise about the difference of precision and accuracy. So here is, what is this? Not too accurate. This is not too precise. So more accurate is to the left, but more precision, and more precise is to the left, I'm sorry. See, I got it wrong, at least the way I said it. And the accuracy, you know, as you go upward on these graphs, these miss the truth by more. So science is not an exact science. It should be and. Physics. Another point to make is that physics impacts your everyday life every day. So that's an important thing that we like to get. So I want to ask how people got here. I mean, by what means of conveyance? By car. Okay. And did you know the way? Yeah, you didn't need a map or anything. So that's the thing about this crowd, as I look at it, is you know the town too well. But I have been spoken to a lot of audiences where people actually had to pull out their maps, by which we mean our phones, or the nav in our car, navigation system, our car, which uses the global positioning system, which was back in the 1990s, my talk on nuclear magnets said it wouldn't be possible without nuclear magnets. So the GPS system uses a whole number of technologies, all of which emerged from physics research, atomic clocks, which are quantum clocks, the fact that the satellites are all in different positions and that the speed of light at which the signals come from, except for the delays in the atmosphere and so on, at least is fixed, finite, not fixed, because everyone has a different delay. You have to make corrections for the atmosphere. You have to make corrections for the fact that everything's in a moving frame. There are even corrections that have to be made for different altitudes. Then the cellular internet, that whole network of cell towers connected to telephone companies that are connected to the internet. Well, they're not telephones, right? Wireless companies. I don't want to name any of them. You have to get the maps, right? That's actually data, information, magnetic sensors in your phone tell you which way's north. And then there's also the maps have corrections for which way magnetic north is relative to real north, which is what we want. So all of that is in your phone, and all of that comes from physics. Oops. Well, this says, public trust in science requires understanding science, methods, data, and uncertainty. So I'm going to move to talk about data that come from polling and two different sources. One of them is the Pew Center, which does polling and gauges public opinion. And they did a poll in October 2024. And another is from the National Science Foundation, one of the main funding sources that was established in the 1950s to see that the government ensured that science and technology, that was pre-Sputnik, but not very pre-Sputnik, came on. So what we're showing here since 1992 to 2022, so over the 20 years, a good fraction of the last 30, how the public has felt that science, now the GPS system, but then there was sort of different things, and at some point, not long before 1992, there were paper maps. I still have a lot of them. Science makes our way of life change too fast. Okay, so not an insignificant number of people feel that things are going too fast, and I think maybe with AI, artificial intelligence, I can join that, at least right now. I'm not keeping up, I know that. And I think probably that's the point. Science provides more opportunities for the next generation. That's a very optimistic way of looking at science and technology, and that is, you have to ask yourself whether 80% is a good grade or not in this. And I don't know the answer to that, but I'm going to show you the data. Federal government should fund basic scientific research. Gosh, I could go faster. And that is also fairly strong. I'll just keep going through this. How often U.S. adults thought about the impact of science on their everyday lives? Okay, every day. A lot, a little, never. So basically, it's not out of something that people don't think about, but not really a lot. I think about it all the time, of course, but that's what I do. So demos are an important part of Saturday morning physics. This list is incomplete. You can help me complete it, but I know some of the things we do with demos. And this is Monica Wood. She's now the exceptionally capable leader of what's called the demo lab. The room I showed you, Weiser 170, below those seats is her office. And shelves and shelves of devices, and she gave me one to bring here, or two actually, to show you, so I'm going to do that quickly in a bit. Okay, so we do it to teach physics. It's engaging. I hope you'll pay attention, and we'll see often exciting and entertaining. So here's the demo. All right, so what I have here is a device which I'm going to use a number of terms to describe. First of all, it's going to be plugged in, a normal plug. Okay, so I'm plugging it into, well, if you were at home, it would be the wall, but here it's the podium. but nevertheless it fits. And that is alternating current. It's 60 cycles. We still use it a lot in our homes. It probably only matters for the dryer and the refrigerator and charging your car. Anyway, and so there's a button here. And that frequency that you hear is about 60 times per second. And what's happening is current's going back and forth, electric current. And when electric current goes through a wire, it makes a magnetic field. Here, under the tape, are a set of iron rods. And that magnetic field would rather go through the iron rods than go through the air. So it's concentrated in the iron rods. And it's stronger at the bottom and weaker at the top. And that has some really interesting consequences. This is just to make a smooth surface for reasons you'll see momentarily. So I have a ring here, okay? A ring on a string, though the string, try to protect my computer a little bit. Okay, so the thing is that it can be levitated. All right, I don't know if that's surprising or not. Woo. You know what, the thing is, I got distracted because I have a bunch, it surprised me. I have some magnets here, and they started dancing. I should show that to you. I have a way of doing that. I'm sorry, Andrew, I don't know about the timing, but, well, I'm doing great because I'm not done yet. Okay, so I'm going to show you, and you can leave anytime. I have a way of showing, can you see these little things here? I'm going to use them later, but they're magnets, and they're starting to dance. They were in a special place. 60 times a second. All right, anyway, that distracted me. So I was doing a demo. Yeah. So back to PowerPoint. Anyway, so I levitated it. And the string isn't holding it up, obviously, right? It's the magnetic something that's holding it up, right? What's happening, well, I'll describe it in a minute, but if I let it, instead of just fighting gravity, it is a little warm, by the way, instead of just fighting gravity, this device, I let it accelerate, that's what happened, right? and I can catch it. So that's supposed to intrigue you and surprise you, and you're going to want to know what's going on, right? What is going on? Intrigued? All right, so let me explain, okay? I told you this is a magnet, right? It's an electromagnet because it has current flowing through it. And apparently there's a repulsive force of one magnet on the ring, right? So how does a magnet repel something? That something must be a magnet. It's not a magnet now. I can also take this magnet here and trust me, it's a magnet, but it's not attracted. This is not a magnet. Okay. That magnet is attracted, right? All right. So, good thing it's a small room. It's not a magnet until I turn on the current. And then it becomes a magnet and gets repelled. I've been practicing. So what's happening is that the current's going back and forth 60 times a second. Magnetic field's stronger down here, but when the current changes, the magnetic field changes, and a changing magnetic field induces a current, which makes an electromagnet out of this, okay? Only when it's on. And it is an electromagnet such that it's always repelled. we can call that diamagnetism. Dia is in the word diameter, which means opposite. It's the line, the secant that goes across the circle. And so it's diamagnetism. There's always this repulsion. Now, there's a few other sort of interesting things about it. There's an induced current in the ring, and that's an induced magnet. There's a lot of applications of this, a tremendous number of applications, really, really important ones like electric guitars, right? Or maglev trains. The braking of, this is a Cedar Point, one of their roller coasters at Cedar Point. If you come to Saturday Morning Physics at some point, probably if you come in December to our 30th anniversary show, we'll show you a railgun that we built that uses a magnetic field to propel a projectile. This gets warm. You can do it in a way that gets so warm that you can weld with it, which is being done here in a pipeline. Induction cooking, charging, induction charging are just some of the examples of applications of this very same principle, broad applications affecting our everyday lives. You know, so I hope at least a few of these are in your everyday life. Not the railgun, but hopefully the electric guitar. All right, and transformers. This really is a transformer. It uses induction. Transformers that are crucial to transmitting electricity from the power plant, wherever it is, even if it's a solar cell array or a wind generator in most cases, even if it's on your roof. But for the most part, on an industrial scale, it needs to be transmitted, the electrical power, at high voltage. But we can't use it at high voltage, so we have to reduce the voltage. So I have here an illustration of the real, you know, sort of transformer aspect of this. Here, I've turned it on, and this is just a ring that shows you that the electrical current is flowing and making the light bulbs. And you can even see that it's stronger at the bottom than at the top. Okay, so that's a transformer. This is a fixed number of turns, and this one's pretty cool. It's not exciting, but it's cool. So there's a light bulb here and a loop, and I'm gonna actually put 5 turns. Help me count. 4, 5. Shoo. Okay, 5 turns here, and turn it on, and you can see that I'm transforming the voltage from the wall through this device to this bulb. Now, I'm going to go to 10 turns, twice as many turns. What do you think is going to happen? You think about that while I count. Don't interrupt me. 6, 7, 8. I hope not. 9. All right, there's 10. All right. Well, you don't have to say it out loud, but you do have to tell me if you got it right. Everybody have an idea what's going to happen?
It gets brighter or it don't come on?
Is brighter, right? So we've created a larger voltage or current through the bulb, but a larger voltage across the bulb, just to be really precise, with more turns on this is called the secondary of a transformer, and down here the white wires are the primary. Okay, so that's you know, you could say we wouldn't be here without this. It's probably accurate in a lot of cases. Okay, moving forward. There's much more, the magnetic resonance imaging. I want to show you this because it's so much fun. You can't do physics demos without liquid nitrogen. That's not liquid nitrogen, that's water droplets. White, right? All different sizes. And back to the oh, hi. All right, can you see that? All right, so what I have here is a material that's has this property called superconductivity when it's cooled to the temperature of liquid nitrogen. Superconductivity means basically that currents can flow wherever they need to without any energy. Okay, it takes no energy, except it took energy to make the liquid nitrogen, and now the liquid nitrogen is cooling this material. Barium, yttrium, cobalt. Lou can help me with all that. Anyway, it's a special kind of ceramic. And cooling is also really an interesting process. You can see that the nitrogen, which is a liquid, looks like it's boiling. It is, right? It's touching something that's warmer, okay, hot. And so you put water on a stove, and eventually it boils. When it boils, it forms these bubbles of water vapor. And this is nitrogen vapor, which is the largest component of the atmosphere, about 80% of the atmosphere. But the thing about cooling is that it stopped boiling. And the reason it stopped boiling is because they're now at about the same temperature. And when the nitrogen was between the liquid and the device, the piece of material that we're cooling, it insulated it, so it didn't cool as fast. But now I know it's cold because it stopped boiling. Let's put a little more nitrogen there. And this is one of those magnets that I had. And since currents can flow in this material unimpeded, okay, supercurrents, sometimes we might call them, I have a magnet now, and I'm bringing it towards the material, and that is changing the magnetic field in the material, and currents can flow, they do. It's a little difficult to get it the first time. I don't know that I've ever gotten it the first time. There. So can you tell that it's suspended again? Yeah. So that's perfect diamagnetism. And just fun. And intriguing. All right. It'll be there. Because
say that if you flip it, by the magnet flip it, that piece can still stay there. If you flip the magnet, you flip the superconductor upside down.
oh, this
that
thing.
magnet still stay. If everything's cold enough. Okay, sorry.
All right. Well, we have a question and answer period afterwards, so. And I've got lots of liquid nitrogen. There. Okay. I have a picture of that, which, but hopefully you had a sense of it. So that was my camera.
And the styrofoam is inert.
The styrofoam is a good insulator. That's why we use it. Thermal insulator. Okay. Right, so here's an explanation. A superconductor becomes a magnet. The magnet is just perfectly always opposite. This is the induced magnet, this is the actual magnet, so it's always repelled like that. The North Pole, perhaps, against the North Pole. Back to policy, science impacting policy. Two decisive World War II technologies, more about things that affected our life. But these were defensive, radar, and this is at a museum near MIT in Concord, Massachusetts, Lincoln Labs. And this is an actual only color picture of the very first atomic bomb explosion, the Trinity test. But we use this, of course, in weapons, but nevertheless, nuclear fission for power, propulsion of subs, medical isotope production, and producing isotopes that are used to detect neutrons in non-proliferation. Just some examples. Of course, radar, aviation. If you didn't use GPS to get here, have you looked at the weather on your phone today? Weather tracking, mineral surveying. My car drives itself almost. It gets mad at me when I take my hands off the steering wheel for a little while. So science, scientists, and policy. I want to give you my perspective. I decided I need to stick my neck out just a little bit more than usual. So, but I do show this to my classes. about how policy has many elements to it. Policy are the things that, that the government does to affect and improve our lives. And economics should matter, science and data should matter, social factors, for some people it's religions or beliefs, and then politics, in my definition, the red thing, is really about getting elected. In this Venn diagram, and policy is some kind of thing. So we can discuss this afterwards if you'd like, but with that in mind, that thing in mind, here's some more polling data from October. Half and half think that scientists should focus on establishing sound scientific facts and stay out of policy debates. And half think that scientists should play an active role. Since World War II, after World War II, scientists, it was just recognized that, you know, government needed to consult scientists a lot. That attitude in the public apparently is not supported, and it's actually dissipated. There were very notable people who were in the Rolodexes of cabinet secretaries, et cetera. Here are some data about this is from the National Science Foundation. It's 2024, but the data are from 2022. But it shows the trend over time, and I think this is pretty interesting, of how much the public has confidence that scientists will act in the interest of the public. And again, you can decide what's a passing grade here, but somehow I think that if 20% of the population doesn't think that scientists are doing good, then scientists have work to do. It's one of the roles of Saturday morning physics. So this is 2016 and this is 2022. It's really interesting to me that this is a fair amount and a great deal. So that's the two things, an A and a B, maybe. And this peaked while we were all terrified of COVID. The trust and idea that the public needed scientists peaked. And before and since, you know, sort of symmetrically, we're back to where we were. We could, you know, parse this a little bit more, but we don't need to. The point is clear. The impact of COVID, though, is after COVID in 2021, right? So we started coming out of it. There were quite a bit more, were more appreciative, so that's relative, more appreciative of science than we're not. And then some people weren't moved in the 8th. So when I hear about public trust in science, I think about public trust in science. People say, well, I don't trust scientists. If you ask them that question, 20% apparently say no in some way. But do you trust plugging things in your home? Do you trust weather forecast? Right? Would you bring an umbrella if it said it was going to rain? Do you trust asteroid and space junk tracking, a bridge that you crossed to get here? Now that, I imagine that everybody did. Did you trust this building not to collapse, this beautiful building? We're trusting, right? That even walking in the door, your vision correction. Do you trust your doctor? Do you trust public health? So I think the answers are probably more than 80%. Have to, right? You can't live without the trust in those things, which means we're trusting science. This is the over time, just Pew's public trust in science. Now I'm showing this because I'm going to break it down to make a point. So this is the same on the left, which is, you know, still around averaging 80, but it shouldn't ever be going down. However, among, maybe the green we should look at, among people of one political party, it is notably different, right? So the general public is not where we need to look. What we need to look is in breaking it down in various ways. 90% of the radical left, if I could say, trust science, and significantly less of the not so left don't. And then also that other ways to look by by party identity. Particles, much easier to say. Okay, so the future, it's not bad, right? It's in 2016 and in 2024, generally the overall population, it looked the same. But I think we need to worry, right? I mean, I don't need to provide any very specific evidence of things that happened even this week, but opinions are changing fast, and they're hard to track. They're identity-driven, as we showed. Science funding is, at the best, brutally uncertain right now. People are losing their funding. People are not losing their funding, both of which are surprising. I'm sure that young people who we need to keep going in science are wondering if science and being a scientist is a viable career, much more so than certainly when I grew up, in spite of the household that I told you about that I grew up in. I realized there was this wave of COVID students, those of us who teach, or maybe have kids or grandchildren, are aware that was an impact on learning and the way people are learning and the way we are teaching and how we are adjusting to this. And that's a kind of a wave that's moving through. And there will soon be a wave of people wondering about science as well. And I'm not actually, because of time, but I'd love to talk about this in the question period, the gold standard in science. So, Saturday morning physics, now I know. Can I have 5? Saturday morning physics, back to Saturday morning physics. There have been over 300 presentations. There are 281 YouTube videos. The largest one is pretty modest if you look at YouTube videos. It was Sean Carroll, who we were lucky to have give a Saturday morning physics talk because he gave another physics lecture on Friday. He has videos with millions of views, but his video with us is 129,000. So that's where we are. Until COVID, we filled that room, as I showed you, every Saturday. By the way, it costs about $4,000 a lecture, so it really is a significant thing. It's worth saying. And the largest cast and crew in this whole thing was last spring, 23 physics, astronomy, engineering, undergrads and graduate students in physics and applied physics led a show called Good Vibrations, and here are their names. And I'm taking this opportunity to point out, in addition to the names of the students and their affiliations, and it was wonderful. Some of you may have been there. The feedback was tremendous. It was family friendly. Kids came down and did demos with the students. Our Monica Wood, whom I mentioned, and Nick Arnold at the time, Connor, who's just recently left and been replaced, but Carol Raybook has been...
She's awesome.
And last year, her assistant was Sarah. She has a new assistant this year. So Carol has been the anchor and the stalwart supporter and greeter, and we love her. So there have been some big changes over time. Day one was a big change, the faculty lecture series. Donuts, we went to bagels for a while, but then, you know, that budget. Back to donuts. Special funds, we have endowed funds and gift funds. There are graduate student talks, which are really tremendous. COVID, and then our annual family-friendly events. It's not just physics, chemistry, geology, biology, biophysics, technology. We've had a talk on mRNA vaccines, science policy, nuclear proliferation, art and science, an art exhibit that was in the Natural History Museum. The artist came and gave us a Saturday morning physics talk. Now, I don't have any favorites, not even mine. But there's, is this going to work? This is our jingle, if you look at our YouTube video. Can you hear that on the, through my microphone? Yeah. Okay, and I'm just going to give you clips from a few more. Well, that's not working. Okay, so one of the really amazing ones that filled, we had about 600 people. We filled both lecture halls and an upstairs room, was when Keith Wiles told us about the discovery of gravity waves, which the event, which is shown here, took place on September 15th, 2014, and was announced. So that was and was announced in March of 2015. So I want to show you real quickly.
This is to mimic the behavior.
This demo.
Of a gravitational wave that is being emitted by two inspiraling compact objects. All right, now this is a mechanical analog, of course, but it actually has some of the same flavor. It has the same flavor. Oh, here it is. That mathematically and auditorially that you would have from an actual gravitational wave. You're going to hear something that's analogous to the chirp. So let me. Okay. Thank you, guys. This is to.
No, you can build that at home. Okay, so we had a cartoonist, which I'm not going to go into. We had Brad Orr doing hockey.
And scoring.
And
Today
what
I'm
he
gonna
did
put
was
a piano across the room, which is 4 feet. Sean's going to protect it. I'm going to score on it. We have a bow and arrow here.
He didn't have a
and
hockey
special
stick, he had a
puck.
bow and arrow.
And I'm going to shoot Sean with this, and hopefully I'm going to score. Are you ready, Sean?
One year I was in charge and realized that Halloween fell on a Saturday. Saturday fell on Halloween. So we did a physics of Halloween, family friendly. You can see it on YouTube. I'm not going to do that. Josh Cassada, it's astronaut, Navy captain, and test pilot. And here he is on the space station, and here he is back on Earth. And here I am trying to interview him while he's on the space station. And maybe the most remarkable thing about that.
Well, you can. Not everybody does, but you can.
Sorry, I got to go to the beginning.
You can. Hey, Dylan. Well, you
Oh, that's
can.
the wrong one.
Not everybody
Okay.
does.
Sorry. I had to wait and wait because we didn't know when the link would happen. Talk about dead air.
University of Michigan, Saturday morning physics. This is the International Space Station. How do you hear?
Hi, this is Tim Chuck. I was supposed to say loud and clear, but I didn't. At any rate, there were long time delays. So that was a remarkable thing too, and if you like. This is our fall lineup. Aaron Leonhardt, who said the speed of sound and the speed of fruit, the speed of light, was supposed to give a science of baseball talk, and he hasn't. I gave one in 2013, and it will be spiffed up with hopefully some of Aaron's help. And I have a torpedo bat. Aaron invented the torpedo bat, if you've heard of that. Ann Curzan, our former dean, the host of NPR's That's What They Say, will talk about physics language. How old is the universe? Former Michigan fellow at Syracuse University, Society of Fellow. What is classical and quantum in physics? And then our 30th anniversary, the demo lab will take over. So, also it's 100 years since spin was invented, and we're having a special event that I'm also helping organize on Wednesday, November 3rd. And thank you, and please come to Saturday Morning Physics. And thanks for letting me talk for so long.
Saturday is misspelled.
Yeah, I could believe that.
Well, I have a lot of questions, but I'm only just going to ask one, and then we'll turn it over to the audience. And the question I want to ask is, well, I'm going to go with the one you sort of prompted me to ask. What do you mean by the gold standard of science?
The gold standard of science is a term that was, to my knowledge, in this context, first used in an executive order that President Trump signed in May, I think May 23rd, that laid out 9 principles of science to restore public trust in science. And I think if you, I agree with them completely. They include, I can't get all 9. I have a list of them if I could pull up the slide, but they include a testable hypothesis. They include reproducibility. They include peer review. So they're all very, very reasonable. And hopefully that's, and I've heard the term, so that's why I researched it. I've heard the term used by the Secretary of Health and Human Services and by the White House press secretary, that we will only use gold standard science. So we'll see, or maybe we have this week. But it's correct. One of the things about the executive order and also the White House reporting of it since then that worries me is that the motivation is to restore public trust in science. I showed you numbers that show that it really hasn't moved much. The 2 examples that they give are the mask and school closings during COVID, which happened in the first few months and lasted a few months, I guess. But nevertheless, and science is blamed for that. That's policy. And so that is already a concern in that. The other example, I won't get completely right, but it had to do with the impact on some fisheries due to imperfect data on species of whale. And that was the other example they used. And so that I don't have that much to say about. It could indeed be, and it's not surprising because science is not an exact science. And so counting whales, basing policy on counting whales, that is policy. And I think the scientists are responsible for the data, for interpreting the data, for making sure that if there are open questions, that that's part of the interpretation of the data. And that's certainly the way it should go. So I don't see how those 2 examples necessarily hold up to, at least the one about COVID has much to do with gold standard science.
Thank you. I could be very selfish and rude, and I want to be, but as a good host, I think I'll open it up to questions from either our audience right here in the observatory or through the live stream. If you have live stream questions, please just enter them in the chat. If you're here, please raise your hand and wait till Greg Parker there brings you in a microphone so everybody can hear you. Well, then I'm going to ask more questions.
Brandon.
Oh, wait, sorry, we have one in the back.
It's always great hearing about the history. I think I go back maybe 20 years, so I didn't get the benefit of all 30 years of S&P. But from the years of attending, I always think about like how important the legacy is of especially physics and science of demonstrations. Because if you look at 100 years ago, 150 years ago, a scientist would make a discovery, and one of the first things they do is do a public demo. And that's one of the things I love most about Saturday morning physics, and personally I think we need more of, is, hey, here's a way to communicate what we're doing as scientists, and I think that also engenders trust. So my question, though, is, kind of building on that, every time I attend, I'm like, how do more people see this? So I'm sure you guys think about the same thing, and like, beyond YouTube and other things, have you guys thought about the future of just disseminating this more? I know there's been some, I think, of these on public TV. We'd be curious to hear just like you know, because there's some stewardship, I think, of creating something as special as Saturday Morning Physics. So how do you see kind of getting the word out there more?
So I have two things to say about that. One is about Saturday Morning Physics, which was developed for this community, and I think we are successful in that regard. I would love, given that we have YouTube videos and everything else, if lots of people watch them. They are hour-long presentations, et cetera, so that it's not something in a nutshell. It's not the way people necessarily consume information right now, but nevertheless, it is what it is. So that is our product, and that is the value that it has. And I am very pleased that our online audience, which is very faithfully 100 people, they ask very good questions in our question and answer. This all started with COVID, that we now live cast them. And I think that was a really good thing. There are fewer people in the room, you know, but I think overall that it's about the same, and it's the same community. We have fewer schools involved, and we have an understanding of how busy teachers are and the demands, and something extra, like some teachers used to bring groups of kids on Saturday mornings, and we haven't seen that in a while. And I have not signed an extra credit form in maybe a decade. So I should talk to the Ann Arbor teachers who are friends of mine, some of them. All right, so in the bigger picture, there are a few what might be called public scientists who have a very important role because lots of people listen to them. And they need to, I think they should be talking more about the policy related things that I brought up as a, you know, maybe it's the first time. I mean, I really wanted to make that part of this talk. So Sean Carroll, and we know who there are. There's also, I don't know exactly what the listenership of public radio is, or it used to be science shows on public television. Now there's so many options, but those are ways that the broader message can get out, and these people have the attention, and when they talk, people listen. Lots of people listen. So it's really important for them to make it clear not just what's, you know, sort of deep about quantum mechanics, but what's important about the way we do science and the impact that science has.
Back in 2011, Dr. Frank Hsu gave a very convincing argument for thorium reactors. And interestingly, he only spoke for an hour, but the video is 2 hours long. And I don't understand how that came about. And I was just curious as to how much extra material was stuck into the video.
Well, the video people are actually in the room, but we won't put them on the spot. I don't know. I will look at the video and get back to you on that. That's very interesting. I'd like to say there was a simple explanation, you know, like time dilation or something, gravitational redshift, but I don't think that's it. Yeah. I consider that a simple explanation.
Your inner physicist is showing there, so. Time for maybe one more question?
So I was wondering, building off the last couple questions ago, what do you think regular scientists, not public-facing scientists, should be doing to increase public trust in science? Do you think that's part of something that should be part of our work? And is things like Saturday morning physics part of that? Is it enough?
Well, there are a number of things to say about that. It's not a typical part of a career path in science. There are early career awards that the Department of Energy and the National Science Foundation, NIH, that actually have had a public engagement component as a requirement of that to encourage people to one way or another consider how to communicate more broadly and have a broader impact than just the product of research itself. But I think also it's fair to say that in the academic world, and I'm not that familiar with the industrial science research, and it's different now than it used to be, and the national labs, that public engagement is appreciated, not discouraged, but not really a component of the career path. So when I took part in this extravaganza, as we called it, with 23 students presenting not research, not cutting edge science, but just explaining science, they loved it, the enthusiasm, and that was part of the idea, was to, some people will get hooked, and then I was. But does that answer your question? I think, yeah. But we'd love to, encourage you.
Well, we're almost out of time, but I just wanted to say thank you all for joining us this evening. Thanks as well to Greg Parker, the director of this wonderful observatory, for monitoring the live stream over there in the corner. Thanks as well to the Michigan media team for recording and live streaming the session this evening. Tonight's session will be available on YouTube in about a week. It will be shared automatically with everybody who registered. I'm also happy to send links out. I'll send one to you tomorrow. Our next Making Michigan will be on October 16th, when we'll be joined by shipwreck researcher and documentarian Rick Mixter. We'll be discussing the 50th anniversary of the sinking of the Edmund Fitzgerald and some surprising connections with U of M and the Bentley Historical Library. As Professor Chubb was telling us earlier, the first Saturday morning physics of the season will be next Saturday. Go out and learn all about baseball and, why the Tigers are collapsing as we watch. If you're here at the observatory, the original observatory upstairs will be open briefly until about 8 o'clock. It's also open for viewing nights every Thursday and Friday. Please join us again if you're watching us online. I hope you can join us soon. And on that note, have a wonderful evening, and thank you again. Well, let me turn off my microphone.